Hello everyone. I am your course instructor Monisha Raj.K.H, Assistant Professor, Department of ECE, Sai Vidya Institute of Technology. In this lecture video, we'll be continuing with Module 1 of Information Theory and Coding. In this lecture video, we'll be seeing about the properties of entropy, extension of zero memory source, and we'll be seeing numericals on that, as well as we'll be seeing an derivation about the relationship between Hartley bits and nets. So first, let's see the properties of entropy. The first property of entropy is entropy function is continuous for every independent variable pk in the interval 0, 1. That is, pk varies continuously from 0 and 1. Entropy function vanishes at both pk equal to 0 and pk equal to 1. This is the first property of entropy, that is, it is continuous. The second property is the entropy function is symmetrical function of its arguments. Here we are talking about the arguments. So it tells that h of pk, 1 minus pk will be equal to h of 1 minus pk, pk, irrespective of the position of the arguments for all k equal to 1, 2, 3 up to q. This is symmetrical function. The third one is extremal property. What do you mean by extremal property? Entropy attains a maximum value when the source symbols becomes equiprobable. That is, h of s max equal to log q to the base 2 bits per symbol, where q is the number of symbols in a sequence. This is extremal property. The fourth property is additive property. Additive property tells that the partitioning of symbols into subsymbols cannot decrease the entropy. That is, h dash of s equal to h of s plus a positive quantity. Also, h dash of s is always greater than or equal to h of s. The fifth one is the source efficiency. Source efficiency is given by the ratio of entropy of the source to maximum entropy of the source, and is given by eta s equal to h of s by h of s max. We've already seen h of s max in third property. So source efficiency is h of s by h of s max. The sixth one is source redundancy. Source redundancy R eta s equal to 1 minus eta s, where both eta s, that is source efficiency, and R eta s, that is source redundancy, are expressed in terms of percentage. Remember, source efficiency and source redundancy will always be expressed in terms of percentage. These are the properties of entropy. Next is, we'll be seeing about extension of zero memory source or memoryless source. What do you mean by zero memory source or memoryless source? It is a type of source in which there is no connection between any two symbols and that the source has no memory. Extension of zero memory source becomes a necessity in some of the coding situations. First, let us consider a binary source S emitting symbols S1 and S2 with probabilities P1 and P2 respectively, such that P1 plus P2 equal to 1. Then the second extension of binary source we have, or the number of basic source symbols extension will have 2 power 2 equal to 4 symbols. It's 2 power 2 here because we have only 2 symbols. If we have 3 symbols, it will be 3 power 2 symbols. It will always be square of number of symbols present. Okay, now let us see how to calculate the probabilities of these second extension symbols. So first is S1 into S1. The probability of S1 into S1 is P1 into P1, it will be P1 square. Second one is S1, S2. It will be P1, P2. So probability of the second one will be P1, P2. Third one is S2, S1. S2, S1, the probability would be P2, P1. And the fourth one would be S2 S2. The probability will be P2 P2. That will be equal to P2 square. So the sum of all the probabilities of the second extended source is equal to unity. That is P1 square plus P1 P2 plus P2 P1 plus P2 square equal to 1. We can write this also as P1 plus P2 whole square equal to 1. This is how you find the probability values for second extended source. Next, we need to know how do you calculate the entropy value for the second extended source. We have already seen the entropy of basic binary source. We'll just see once again about this. That is, the entropy of basic binary source is given by h of s equal to summation I equal to 1 to 2 pi log of 1 by pi. Where here we are considering only two symbols, hence the summation limits would be I equal to 1 to 2. So P1 log of 1 by P1 to the base 2 plus P2 log of 1 by P2 to the base 2. This is the entropy of basic binary source. Next, we need to see the entropy of the second extended source. Here the symbols are 4, hence the limit of the summation would be I equal to 1 to 4 pi log of 1 by pi. It would be P1 square log of 1 by P1 square to the base 2 plus P1 P2 log of 1 by P1 P2 to the base 2 plus P1 P2 log of 1 by P1 P2 to the base 2 plus P2 square into log of 1 by P2 square to the base 2. This is about the extension of zero memory source. Next is, we'll be seeing a numerical on that. First, we'll see a numerical on efficiency and redundancy. A discrete source S emits two independent symbols X and Y with probabilities 0.55 and 0.45 respectively. Calculate the efficiency and redundancy of the source. So here they're asking you to calculate efficiency and redundancy for the two probability values given as 0.55 and 0.45. So the steps to be followed is, first you need to calculate H of S, then maximum value of H of S, then source efficiency, then source redundancy. So we know the formula for H of S. So we'll see, as there are only two symbols given, the summation limit should go as summation I equal to 1 to 2 pi log of 1 by pi to the base 2. So P1 value is 0.55, P2 value is 0.45. So substituting those values, we get it as 0.55 log of 1 by 0.55 to the base 2 plus 0.45 into log of 1 by 0.45 to the base 2. So H of S value after calculation, we get it as 0.9928 bits per symbol. This is H of S, that is the entropy of the source. Next is maximum entropy of the source, where this we have seen in properties of entropy. So maximum entropy is given as H of S max equal to log Q to the base 2, where Q is the number of symbols present. So here there are only two symbols, so Q value will be 2. So log 2 to the base 2, where it will be 1 bit. Then source efficiency formula is eta S equal to H of S by H of S max. We have calculated H of S and H of S max value, substituting those values 0.9928 by 1. So eta S will be equal to 99.28%. Remember, you need to represent it in percentage. Next is source redundancy. R eta S equal to 1 minus eta S. So eta S value is 0.9928. So R eta S would be 0.72 percentage. So here also you need to represent it in percentage itself. This is about efficiency and redundancy. Next we'll be seeing about second extended source. This is another numerical. Consider a discrete memoryless source with source alphabets S equal to S1, S2, S3 with probabilities P equal to half, 1 by 4 and 1 by 4. Find the entropy of this source. Also determine the entropy of its second extension and verify that h of s square equal to 2 into h of s. So here they're asking you to calculate the entropy of the normal source and the entropy of the second extended source, and they are asking you to verify that h of s square, that is the second extended source, will be equal to twice of the normal entropy value. So first we need to see how to calculate the basic source with three symbols. So h of s equal to summation I equal to 1 to 3. This is because we have three symbols. So substituting the values, 1 by 2 log 2 to the base 2, and there are two 1 by 4 values. So 2 times of 1 by 4 into log 4 to the base 2. So calculating h of s value, we get it as 1.5 bits per symbol. This is simple. Next, we'll see how to calculate the second extension, second extension of basic source with three symbols, and how to verify h of s square equal to 2 into h of s. So as we have three symbols here, it will be the square of number of symbols. So 3 square will be 9 symbols. How will I calculate that? So S1 probability value of S1 would be half half. So half into half, it will be 1 by 4. Next is S1 S2. S1 S2 1 by 2 into 1 by 4, the probability values. So it will be 1 by 8. So S1 S3 1 by 2 into 1 by 4, it will be again 1 by 8. S2 into S1 1 by 4 into 1 by 2, it will be 1 by 8. S2 into S2 1 by 4 into 1 by 4, it will be 1 by 16. S2 into S3, it will be 1 by 4 into 1 by 4, 1 by 16. S3 into S1, 1 by 4 into 1 by 2, it will be 1 by 8. S3 into S3, it will be 1 by 4 into 1 by 4, it will be 1 by 16. S3 and S3, the property values are 1 by 4 into 1 by 4, it will be 1 by 16. So these are the probability values for the symbols, 9 symbols for second extension of basic source. Now we need to calculate the entropy. So h of s square equal to summation j equal to 1 to 9, as there are 9 symbols, pi log of 1 by pi to the base 2. Now you need to substitute the values. So how many 1 by 4s are there? There is only one by 4. So it will be 1 by 4 into log of 4 to the base 2. How many 1 by 8s are there? 1, 2, 3, and 4. So multiply 1 by 8 into log 8 to the base 2 into 4. How many 1 by 16s are there? 1, 2, 3, and 4. Now substitute 1 by 16 into log 16 to the base 2 into 4. After calculating this, we get the entropy value of the second extension of basic source as 3 bits per symbol. Now they've asked you to prove it. So how do you prove it? H of s square equal 2 into h of s. We know the value of h of s square and h of s. So substituting those values, h of s square is 3 bits per symbol, h of s is 1.5 bits per symbol. Substituting and calculating, we get it as 3 equal to 3, hence proved. Note that sum of the probabilities of the second extended source symbols must also be equal to 1. Remember this. Always the probabilities of all the symbols should always be equal to 1. This is one important thing. Next is, we'll be seeing the relationship between Hartley bits and nats. So, by the definition of self-information with respect to nats, bits, and Hartley, it is given by the definition of Hartley bits and nats, the self-information would be given as I equal to log 10 of 1 by p Hartleys. This is representing Hartley. Bits is I equal to log of 1 by p to the base 2 bits. Nats, I equal to log of 1 by p to the base e nats. First, we'll find the relationship between Hartley and nats. For that, we need to write it as 1 Hartley equal to I by log of 1 by p to the base 10. That is from this formula. Okay. Next is, we know that we are finding the relationship between Hartley and nats. So here substitute this I value with this log of 1 by p to the base e nats. Right. Next, taking these p values to the numerator, we'll get minus sign in both numerator and denominator. So cancelling those minus sign, we'll get it as 1 by log e to the p by 1 by log e log 10 to the p. This is by the formula log b by a equal to 1 by log ab. Log ba equal to 1 by log ab. So see, in the numerator it's p and to the base it's e. So by using this formula, we can also write it as 1 by log e to the base p and 1 by log 10 to the base p. I hope till now you guys have understood. Next is further simplifying 1 Hartley equal to log 10 to the base p log e to the base p. That is taking the denominator value to the numerator and numerator value to the denominator. Further simplification. Now as the bases are same, that is p, we can remove those bases and write it as log 10 to the base e. Okay. This is nothing but ln 10 nats. That is e is represented as ln 10 nats. Then simplifying this, we get it as 2.30 nats. Hence, 1 Hartley equal to 2.30 nats. Similarly, the relationship between Hartley and bits is 1 Hartley equal to log 10 to the base 2 bits. Therefore, 1 Hartley equal to 3.32 bits. In the similar way, we can also find the relationship between 1 bit is equal to how many times of Hartleys. So 1 bit equal to log 2 to the base 10 Hartley. It will be 1 by 3.32 Hartleys. So 1 bit equal to 0.30 Hartley. Next is relationship between 1 bit and nats. So 1 bit equal to log 2 to the base e nats. That will be ln 2 nats. ln 2 nats. So 1 bit equal to 0.693 nats. So how is 1 nats related to bits? That also we can calculate. So 1 nats equal to log e to the base 2 bits. So 1 by log 2 to the base e bits. That will be equal to 1 by ln 2 and that will be 1 by 0.693 bits. So 1 nats equal to 1.443 bits. Then the relationship between 1 nats and Hartley. So 1 nats equal to log e to the base 10 Hartleys. That will be equal to 1 by log 10 to the base e, 1 by ln 10, 1 by 2.3 hats, 1 nat equal to zero point 0.3 Hartleys. Kindly remember, you need to keep in mind or remember these relationship and their values. Sometimes in numericals, they would ask you such questions. In such type of numericals, you need to substitute these values. They would ask you to represent bits in the form of nats, nats in the form of bits, or Hartley in the form of bits, or bits in the form of Hartleys. So for such numericals, you need to remember these values. So next, we'll be continuing with the other topics of module 1 in the next lecture video. Thank you.